Okay, welcome back to video 4 on algebraic geometry. Today I'm going to talk about the Zariski topology. Just kind of gonna, zoom into it here. So as you know, a topology is like it's sort of like a structure of open sets, right? If you've taken topology or if you know anything about it, the one takeaway that you've gotten is you got to define your open sets, okay? And what we deal with here are these zero sets. And so I've drawn a couple of things over here. So this would be a point right here. This would be associated to a maximal ideal in a two-dimensional polynomial ring. This right here, this would be the ideal generated by x. So where x is 0, right? That's going to be your y-axis looking thing. Here's an x-axis looking thing, right? Where y is 0. What we notice though is, especially when we deal with these maximal ideals and the zero sets that they come up with, which again are just points, that's a closed set, right? That's not an open set. It's pretty hard to say, okay, well, here's a point, that's an open set, right? So what it makes sense to do, actually, is to consider these as the closed set. So we consider these zero sets to be closed. And in fact, we can define an algebraic set. That's just a set in the affine space that it happens to be a zero set for some set of functions in the ring. Okay? So all these zero sets are going to be algebraic sets. And if I take any chunk of that ring, generate an ideal, find a zero set, that's going to be a closed set in this topology. So what are the open sets? Well, the complement of an open set is the complement of a closed set is an open set. And so we have that the complements of these closed sets are open in T. And the way to think about that is, if you have a point, say, think about everything in the entire affine space except that one point. Or if you have two lines, think about all the stuff that doesn't touch those lines. So here, all of these four quadrants that are kind of fuzzy, that get really close to these lines but don't actually touch it, don't actually touch them, those are going to be your open sets in the topology, the Zariski topology. So we're going to start with our first example here. This is an example straight out of Hartshorne, and it's it is by definition the most basic example that you have. We're going to talk about A1. This is the affine line, okay? The algebra associated with A1 is going to be the ring of polynomials in one indeterminate, right? And we know some things about this. We know it's a UFD. More importantly, we know that it's a PID. This is a principal ideal domain. In other words, every single ideal can be generated from just one element. So that has a pretty interesting impact on the way that we look at the geometry. Every algebraic set is the set of zeros, right? So every algebraic set is the set of zeros of one polynomial. Right? And as an example, maybe we just take a polynomial from this lovely ring here and find the zero set. And I'll do that right now. So here's a polynomial p of x. This is inside the polynomial ring kx. And the ideal generated by p of x is just going to be all functions q of x times p of x, where q of x is in the ring A, or k of x, right? We've defined this. So what's the zero set of this ideal? Well, the zero set, as you may have guessed already, is just where this polynomial is 0. So it's just x1, x2, x3, x4. Now notice, this is where it gets a little funky, but we've assumed that K is algebraically closed, which means I think using a one-dimensional line is maybe a little bit not correct, but whatever. because, R is not algebraically closed. But this is just for demonstration purposes, so sorry if you hate me, I don't care. This is just for my notes, and that's why I'm explaining that right now. So here you've got your 4 points, right? What you can see here is that this Z, okay, this zero set is these 4 points, and the complement of this zero set, let's just call this S for whatever reason. The complement of this zero set is going to be these intervals here, going out to infinity, this guy here, this guy here, this guy here, and this guy here, going out to infinity. And another thing I can kind of see from this is that I could take, let's say that I came up with ideals for x1, x2, and x3, x4. Well, obviously those would associate to ideals generated by the polynomial with zeros at x1, x2, and polynomial with zeros at x3, x4. And here I've gone ahead and drawn. This is affine 1 again. This is the Zariski set, or the open set associated to this zero set of P1. Again, I've got a 0 at x1, I've got a 0 at x2, and again down here I've got a 0 at x3 and a 0 at x4, which you can see right here. These are just roots of P2. So this is the complement of the 0 set of P2. This is the complement of the 0 set of P1. Now how could we recreate this 0 set, or this complement of a 0 set, with these right here? And obviously we do this by intersection. As you can see, if we take the union of these two, we get the entire affine line. But if we take the intersection, it's going to cleave off x1, x2, and it's going to cleave off x3 and x4, and give us this nice open interval that is associated to z of P1 times P2 complement. So this is more or less an inference that we've made just based on some algebra and some topology. It's not a very deep one, but you can see how there is a relationship that will rely on a lot more. Another example of this is just looking at the maximal ideals. Remember that maximal ideals rise from points, and therefore the maximal ideals associated with these points are going to just look like linear functions, or ideals generated by linear functions like this. And we can sort of paste these together to create larger polynomials. Now this gets much more interesting when you get into higher dimensional stuff, which we will do, but let's keep going for a second. The last thing to talk about before we leave A1 is what happens with the zero function. Well, the zero function is associated with the zero ideal, which is sometimes called omega. I like calling it omega because I don't know why. I can't explain it. But anyway, the zero set of this ideal is going to be the entire space. Okay? So, the complement of the entire space, which is just the null space, not null space, the null set, or the empty set, I guess you could call it. This is naturally open. On the other hand, if I choose the zero set of the empty set here, I then get the hang on just a second. That's what I meant to say. If I take the zero set of the entire ring, I wind up with the null set. I wind up with nothing. And the complement of this has to be open. So A1 has to be open. So you have that both the zero set and the entire line are open in this topology. It's also worth noting that they're both closed. So they're both open and closed.